want to talk about the concept of G's. What is 1G? How big is that? What do G's mean? But first, I need to introduce a new physics phrase. We've given you some physics phrases over the last couple of days. If it says starts from rest, what did that tell you? VI is 0. Comes to a stop. Slows down. A is. Okay, here's your another phrase. If you see constant velocity or constant speed or steady speed, that means A is 0. It means you're not accelerating. As a number, that means A is 0. I'll start to use that phrase. In fact, I think I actually used that phrase in some of the homework already last day in one question. Let's talk about how gravity pulls on things. Near the Earth, if we're in a vacuum, Julius, if we're ignoring air resistance, all objects will accelerate at the same rate regardless of their mass. In other words, Leo, a feather will accelerate at exactly the same rate as a bowling ball in a vacuum. In a vacuum, the feather will not move back and forth like air resistance. It will drop, no pun intended, like a rock. It will in a vacuum. That's very tough for us to visualize because we don't live in a vacuum. So put your pencils down, look up. Pause the video. In a vacuum, everything will fall at the same rate. Everything will accelerate with the same value. We use a lowercase g to represent this acceleration because it's caused by gravity. So we're going to use a lowercase g for the acceleration due to gravity. How big is the acceleration due to gravity? It's 9.8 meters per second squared. Did I give you that on your green sheet? Is that underneath the row that has the 4 kinematics equations? I'm going to say, even though it's on your sheet, you'll be smart to memorize it because you will get sick of looking it up. The acceleration due to gravity on the Earth is 9.8 meters per second squared. If I drop something, it will speed up. It will accelerate downwards at 9.8 meters per second squared. On the moon, g is about 1.6 meters per second squared. On Mars, it's about 3.3 meters per second squared. So it varies from planet to planet. But when we're talking about g's, we'll assume we're on the Earth. People talk about g forces. It's not a force. They should really be talking about g acceleration. In fact, I'm going to go bleh, cross out forces. It's not a force. G's are a measure of acceleration. And so, Mason, you will never hear me say the phrase G forces. You'll always hear me say the phrase, oh, it's because of the G's. Mason, what was 1G exactly? What's a nice round number that's really close to do math with in your head? Yeah, if I'm standing in line at a roller coaster and I want to figure out how fast I'm going to be traveling at the bottom of the first hill, and trust me, it adds to the ride if you know how fast you're going to be traveling at the bottom of the first hill, I'll use 10. 2 G's is 19.6, or about 20. 6 G's is whatever 6 times 9.8 is. 58.6? 58.4? What is 9.8 times 6? 58.8? Wow, I was carrying the 1 wrong. But even 6 G's, you can see Gila, that's still really pretty close to 60. So if I don't have a calculator handy and I'm doing some physics in my head, I use 10. Outside of a vacuum, air resistance can change how fast an object will accelerate. A piece of paper in the air will slowly drift down. So unless the question says include air resistance, assume we're ignoring it. Assume for the rest of the year, anytime we're puzzling something out, it's in a vacuum. There's a phrase, there's a joke, Faith. It says the most terrifying phrase to a physicist is include air resistance. Really? Okay, air resistance is really tricky to calculate. You really need calculus to do it properly. We'll look at it a couple of times this year, but it'll be like It'll be like we're going to be giving a tiger a belly rub. We're going to wear gloves and eye protection and a helmet, and we're never going to let our guard down. And we're going to be very careful because air resistance is just really, really tricky. If you're pulling 3 Gs, that's like having 2 of you dogpile on you. Why is 3 Gs like having 2 of you dogpile on you? Right now, all of you are pulling 1 G. That's the earth pulling you down, and you're used to it. So if you're pulling 5 Gs, that would be like having 4 of you on top of yourself. You'll feel like you weigh 4 times your normal weight. If you're pulling 8 Gs, that's like having 7 times your normal weight. What can human beings handle? Human beings can typically survive up to 25 Gs in most situations, but Ethan, usually anything over 10 will break bones. There's a lot of variation there. It depends where the G's are hitting you from. So your legs, for example, if you're getting pushed straight down or straight up, those can probably handle about 40 G's. But from the side, they can probably only handle about 8 or 10. That's why so often in hockey or football, where there's tackling or body checking, you'll see someone will break their fibula or the tibia. Those are really tough bones to break, but they're not that strong from a side impact. Very strong from a vertical impact. So there's some variation there. At Playland, the ride with the highest G's is approximately... Which ride is that? In Physics 12, we do a field trip to Playland. We go there in May, and we bring our instruments for Amusement Park Physics Day, and we find out. Although you can try and find out if you go to Playland this summer. I said that if we drop an object in a vacuum, all objects will fall at the same rate. When Apollo 15 was on the moon, they made a video of them dropping a feather and a hammer on the moon. So they did Galileo's test.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather.
On the moon is G 9.8? No. So also notice, Ethan, things are going to fall slower. You'll notice it doesn't accelerate the way something would if you dropped it on Earth.
For our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time.
Yep.
How about that?
Hit the ground at the same time and fell slower.
That proves that Mr. Galileo was correct in his findings.
Mr. Dueck? Yeah, Dom? How do we know that humans can survive 25 Gs in most situations? How do we know that anything over 10 Gs will break ribs? We had volunteers experiment on themselves. So I'd like to introduce you to one of my nerd heroes. This is Colonel John Stapp. He was an Air Force doctor, and he was put in charge of designing ejection seats for jet fighters. Keep your phone away, you'll be fine. Because they weren't even sure if a pilot could survive ejecting at a high speed. Well, if the pilot's going to die when you eject, why put an ejection seat in? Force the pilot to try and land, even if there's only a 1 in 50 chance of landing. That's better than certain death. Colonel Stapp could have ordered people, other soldiers beneath him or in rank, to do the tests. He felt uncomfortable doing that, and so Julius, he volunteered for a bunch of these tests himself. Among other things that he did, he rode a rocket sled. In the photo that you see here, he's being subjected to 15 Gs with a peak of 22 Gs in this photo here. But he peaked out here. I like example A, I like example A. Example A is a nice question. His rocket sled was traveling at 0.9 times the speed of sound, or Mach 0.9. It's about 300 meters per second. If he came to a stop in 0.68 seconds, how many Gs did Dr. Stapp experience? Ethan, what's this question asking me to find? I know you're zoning up, bringing you back. What's this question asking you to find? Keep reading. Don't overcomplicate it. Find the phrase that says how many. How many what? Keep reading. How many what? I'm looking for a letter of the alphabet. Okay, so let's try that again. What's this question asking me to find? How many what? I'm going to ask you at least once on the test to find G's. We don't. The first thing, and you were right, Ethan, the first thing we do find is acceleration. Even though it says G's, we're going to find the acceleration, and we're going to convert that. Ethan, what's that 0.68? How do you know? Yes. Oh, you know what we should have underlined, folks? Came to a stop. What does came to a stop tell me? VF is what? Yeah. What's that 300, Ethan? Well, what are the units next to that 300? It's meters per second. So it's a velocity. Is it initial or final? How do you know? Because we already figured out, okay? And that's kind of why I did it in that order. I was like, I'm not so sure what that 300, wait a minute, came to a stop. That's got to be V final. So V initial. Are all my units good or are there yucky units? I always check. Are my units good or are there yucky units? Are there yucky units anywhere? Nope. Okay, let's go, Ethan. Looking for an equation that's got an A, a T, a VF, and a VI in it. There is one. Is he right? Yes, he is. Let's see if we can get the A by itself without writing out the equation on the paper. So stare at it, and I'm even going to say, I'm going to write down A equals. Yes. It's going to be 0 minus 300 divided by 0.68. And now you want to go to your calculators. Is this a fraction? Yes. Is there more than one thing on the top? Yes. Brackets are on the top? Yes. Or use your fancy schmancy fraction button. You're going to get a pretty big acceleration, but it's negative. You get negative 441 and change. Does the negative bother me? Let's see. In this situation, was he speeding up or slowing down? Okay, I'm good with the negative. In fact, that relaxes me. I probably did this right. Now, this is meters per second squared. Not what they wanted. Ethan, back to you. What did they want me to find? How many what? How do I convert acceleration to G's? Well, how big is 1G? I'm going to divide by 9.8. So here's my notation. I write G's equals, and this is going to be my answer button, divided by 9.8. And this is where I said there's a lot of variation, because you'll say, well, wait a minute, Mr. Dueck, that's way more than 25 G's, and you said 25 G's in most cases is fatal. There's a lot of variation. How many G's was he pulling? Negative what? Yeah, again, that's like having 44 of him dogpiling on top of him. Imagine that, okay? And the units for G's, it's technically no units. It's G's. It's G's. Other things that he voluntarily did, so he was able to show that you would survive ejecting, but then the pilot said, okay, what's going to happen to our skin at that speed? So he voluntarily exposed his face to 940 kilometer per hour winds, because if your eyes and your face were going to get ripped off when you ejected, pilots weren't going to eject. So it wasn't going to be worth putting the ejection seats in. I have videos of some of the tests. They're pretty graphic. You can look away if you want, but these are some of the testing that they went through. I'll give you a little bit of play-by-play. So that was their original setup, and that's Colonel Stapp, was, okay, how can we test acceleration? We'll swing into a barrier really fast and have it stop us almost instantly.
In 1947, in the deserts of New Mexico, an Air Force colonel named John Stapp began a bizarre top-secret aeromedical project that would lead to the development of the first crash test dummies.
This is where we got all of our crash test dummy data from. This is how we know how to design and build and how strong to build crash test dummies.
Colonel John Paul Stapp is sort of the father of this business in the sense that he was interested in how to protect air crewmen when they ejected out of an aircraft at high speed.
This is it in real time. This is a massive whiplash jerk on his body. Watch.
And he didn't know any way to study that other than to subject human volunteers to loading that's very similar. Go! One of the rules of human volunteer testing is you've got to be willing to do it yourself. So he was his own volunteer.
Stapp used this high-speed test track for a terrifying series of experiments.
He started the countdown.
5, 4.
Then, just as he reaches 0, you get this enormous ram against your back and feel totally helpless. You're being given the biggest kick that could be delivered.
Remember, there was the old saying in the Army, don't volunteer. And in fact, there were several figures in the early days of this kind of work, before there were dummies, who were doing peculiar things. Several of these people became disabled.
Undeterred by the risks, Colonel Stapp pushed human testing to the limit. He was trying to work out the maximum speed at which pilots could safely eject. During a 7-year period, he volunteered for 26 potentially lethal experiments.
This thing? When you see the impact to come back 25 more times, Mr. Stapp, I take my hat off to you. I never would have done it. What's the name of the rocket sled, by the way? Read the name. He is going to break the sound barrier. Also, you'll notice in the first video, he was in a chamber, but then the pilot said, wait a minute, after we eject, we're going to be in the air. Colonel Stapp said, you're right. We're not going to have a door in front of me. I've got to see what the wind does to me at this speed as well. So he was trying to make it as realistic as possible.
So Dr. Stapp kept going faster and faster, and finally in December 1954, he hit his fastest speed. According to the newspaper, 632 miles an hour. According to the calculations I made from feet per second, at one point he hit 639. But the average would be about 632. And he stopped very, very short. Just a matter of a second or less.
Stapp's record-breaking run made him the fastest man on Earth. He endured a massive 43 Gs during the deceleration.
Now here's what you don't know. I'll tell you what has happened. So when he came to a stop, his body stopped, his eyeballs didn't. They came partway out, popped back in. So what you can't see right now, his eyes have filled with blood, and he's blind right now. He was blind for about 15 minutes after this. He thought he was permanently blind. So there's going to be some graphic video in a second. You can look away if you want.
The equivalent of smashing into a wall at 70 miles per hour.
As he said, his eyeballs just about popped out. His eye started bleeding, and for approximately 10 minutes following his famous run, he could not see. But later in the hospital, his vision started returning. He also sustained blisters all over his body.
Dust particles at that speed. They're like bullets at that speed.
Dust particles impinged upon his skin right through the flight suit he was wearing and raised rather interesting looking welts, which fortunately went away.
In full recovery. In fact, I think He lived to his late 80s or early 90s. So that's Dr. Stapp. The other one, another person working with him, was Eli Beatty. Eli Beatty pulled 83 Gs backwards, which is a little easier on your physiology, but you'll see the video of that. It's pretty intense.
It fell to the lot of two other Air Force officers, John Paul Stapp and Eli Beading, to demonstrate that men could withstand G-forces as they would be experienced during a rocket launch and re-entry. On the Holloman rocket sled, Stapp reached a top speed of 640 miles per hour and slammed to a full stop in 1.4 seconds. He suffered no serious or permanent ill effects from the 55G peak deceleration load he took.
This is the one that we saw. So this is the 83 Gs going backwards, and watch his skull. You're going to see his entire skull collapse, deform, and pop back up.
Beading subjected himself to an incredible 83 Gs in a later test made on the shorter Daisy track. Beading went into a state of shock and for a time was considered to be in a critical condition. 5 days later, however, he was back at work with no permanent disability.
5 days later. Again, I take my hat off to these people, Kobe. They were risking their own lives to help us get better lives.
These and other intrepid human volunteers took risks at least as dangerous as those they had required of the animal subjects. And the data thus gained contributed significantly to the successful flights of Alan Shepard, John Glenn, and their successors.
Yeah, not only did the U.S. Air Force use this data, NASA used this data as they were developing spacesuits and things like that. Back to the notes. Almost done. Where does the value of G come from? We're going to calculate it as a lab in a couple of days. You're going to try and measure it. Turn the page, please. If you want to measure acceleration and G's on your smartphone, there are a couple of very good apps. One is called Physics Toolbox Sensor Suite. It's iOS and Android. You want to make sure it's the one by Christian Vieira. He is a programmer. His wife works for the Smithsonian Museum as an outreach science instructor. So he's written some apps that have all sorts of nice features. It's got decibel sensors and Richter scales, all sorts of neat stuff. Or you can also try Fifox or Fifox. That's from Germany. It's also a really nice app. If you know you're going to an amusement park and you're curious, okay, how many G's am I going to be pulling? Have at it. I think it adds to the ride. If you know you're pulling 3 G's going around a corner, how can the ride be anything but better knowing that? I think it's great. What's your homework? So number 1 is pretty straightforward. Find the acceleration, find how many G's. Number 2, how many of you have been on a launch coaster? That's a coaster that launches from the ground rather than taking you up a hill. Like California Screaming, for example. You've been on one? Playland now has one, but I haven't been on it yet. This is from about 6 years ago. These were the 5 most G's launch coasters on Earth. So what I have for you, well, first of all, what's VI for every launch coaster? Be obvious. They all start from rest. I found the final speed in kilometers per hour. Do we do physics with kilometers per hour? You'll have to convert it to meters per second, but I found the time. How many G's are you pulling for each of these? There they are right there. This one is interesting because you're pulling over 3. I just heard about a year ago, I think this ride might have got shut down because people were breaking bones on it. And it's sad, but that makes me want to go on that ride even more. I don't know why, but it does. Anyways, so it may not be the biggest G's. It may have been shut down. Number 3, I have not done one like this. Suppose you've been hired to design a launch coaster and you want the riders to experience 1.8 G's for 3 seconds. Work your way backwards. So we've figured out how to calculate G's. Can you figure out, if you know the G's, can you work your way backwards? Find the acceleration, work your way backwards, find VF, and find how long the track needs to be in order to accomplish that. Your homework then, take-home quiz is your first goal. You can work on this, but if you haven't finished lessons 3 and 4, you can also work on those. I was hoping to give you half an hour. You're going to get 35 minutes. Let me hit pause.